Okay, hi there. Thanks for joining. Going to be about 3 minutes, and then we'll get going. Topic-wise, it's going to be the carbon cycle. So we'll be starting bang on 6:30. Very much trial and error this one. First live. So still getting to grips with the technology, still getting to grips with how to make the screen more high resolution. You will have to bear with me on the technology front, but experimental, definitely. Okay, so we'll give it a couple more minutes and then we'll get going. Okay, one more minute and then we'll get going. Right, okay, it's 6:30. First live, very much seeing how this works in many respects. Very much seeing how many people jump on. There's currently 0, so what I'm hoping happens is that people join as we go. I know this is being recorded, so this can be uploaded afterwards, but the stuff we're going through tonight is carbon cycle. We're starting right from the beginning with carbon cycle, so hopefully this will evolve into a series, if you like, so if you can tune in each week and I guess develop your carbon cycle knowledge, develop the confidence with the carbon cycle knowledge as you go. So we'll start at the beginning with your fundamental understandings with the carbon cycle. So if you think about it, just like the water cycle, we're thinking about elements of carbon and how those elements of carbon move around the world, essentially. And what makes it infinitely more complex than the water cycle is that carbon can exist in many, many more forms. So if you think about water, that's water there. And the water cycle just kind of, you're really just looking at changes in state. So changes in state being, it's a solid, it's a liquid, it's a gas, whereas carbon can exist in so many different ways, in so many different stores. So in the atmosphere, we've got CO2, we've also got CH4. In the biosphere, so being stored in living things, it can be in the form of carbohydrates, it can be fats, it can be proteins, it can be DNA. These all have different chemical formulas. Can also, if it's in the lithosphere, it can be in the form of calcium carbonate, it can be in the form of fossil fuels, again, specific formula, if you like. In the oceans, again, it can be in just dissolved CO2. It can be in all sorts of different marine biota. So you can see it's infinitely more complex than the water cycle, and that I think is why students really struggle with the carbon cycle at first, is because they think they have to know absolutely everything. You don't. You've just got to know the fundamentals, and you've just got to know the absolute basics. So what comes into this in the initial stages of understanding the carbon cycle is that it exists in this. Okay. Now, just if you are watching and wanting to participate, please do. This is exactly how my online group tutoring works, in that what will happen is I'll ask a question, and if you put something in the chat, then I can respond to it. So anything that you recognize here, please do just interact with it. It'll help me keep going and keep pace. But this sign here means that it exists in, like all physical systems, a dynamic equilibrium. So on this side here, we've got inputs, and on this side here, we've got outputs. So there will be inputs of carbon to different stores. There will be outputs from different stores as well. And there's all the movements in between. So what you've got to know with the carbon cycle is, what are our major stores? And what are the major fluxes? And also included within that, what are the major processes? Okay, so we'll start with the stores. The stores is usually the easiest place to start, and these are the places where carbon, in its many different ways, are held. So welcome if you're just joining us. So I can see there's 4 of us on tonight. So if you just let me know where you're joining from, it gives me a good idea of like where my audience is, and it's just quite exciting to see where people are joining me from. It could be internationally, it could be across the country. So I'm based in Manchester, so it'd be nice to see if people are joining from elsewhere, or former students even. So what have we got here? From Kent. All right, welcome from Kent. Thank you for joining. Yeah. What school are you from? Just out of interest. I think there's quite a few schools in Kent that I'm in touch with. Just let me know your school as well. Right, so the different stores we've got the rock store, which is known as the lithosphere. This is by far the largest store, Now, some sources will say that there's 100,000 gigatons in here. I teach that there's 1 million gigatons of carbon stored in the lithosphere. Now, predominantly, this is stored in the form of sedimentary rock. So that would be calcium carbonate is one example. And the other store is fossil fuels as well, which is definitely something that you need to know about within the carbon cycle. So your fossil fuels, that makes up 4,000 gigatons of carbon per year. So that's your lithosphere. So what we've got to think about is, what are our other stores? We've got the biosphere, so when carbon is stored in living things. Now, another way of saying that carbon is stored in living things is what's called biota. Now, living things can range from vegetation, plant life, through to us, anything living, okay, anything living. So the biosphere can be broken down into the terrestrial biosphere, which is carbon that is on land. And then you've got the marine biosphere as well, which is anything living that's in the oceans. So that's nice and easy. Your biosphere is then covered by the atmosphere store, so the atmospheric store. And the gases that you definitely 100% need to know, CO2, comes up quite a lot in A-level geography, and you've got CH4 as well, which is methane. Okay, Judd Tonbridge, nice. Okay, joining from Horsham. Yeah, good. Right, William, this is really important. So you're doing exactly the right thing in terms of you're joining and you're sort of getting ahead with the carbon cycle, because it's quite a complex topic. It can be quite overwhelming at first. So what this will give you, and what will happen over the coming weeks, is that you will get that first exposure. Not everything will go in, but at least you've got that first exposure, so you know what you're looking out for in the carbon cycle. Like, do you know what, I recognize that. And now when you're in the lesson, you'll have that kind of deeper understanding, and that will get you off on the right foot with it. So well done, you're absolutely doing the right thing. So atmosphere, we've got lithosphere, biosphere, atmosphere, and then we can also talk about it being in the hydrosphere as well, which is the various ways in which carbon's stored in water. Your main stores you're going to talk about are lithosphere, biosphere, and atmosphere. We can break the biosphere, certainly on the terrestrial biosphere as well, into you've got your vegetation stores, you've got your consumers, which are us, so basically anything consuming vegetation, and you've also got the soil store too. Yep, so we've got vegetation, soils, and consumers, living things, animals. It's basically your flora and your fauna. So they're the major stores. So once you know that, then it's really important to know that fundamental concept of residence time. So residence time, I'm sure that some of us will have come across this concept before, residence time. So if anyone wants to put anything in the meeting chat, what do we mean by residence time? So residence time, really important concept in carbon cycle, very important concept in water cycle. But again, meeting chat, what have we got? So residence time, what does that actually mean? If I don't get anything coming through, what I'll do is I'll wait about 10 seconds for something to come through. Someone might want to type something out, but residence time. Nothing's coming through, not a problem at all. So residence time is how long something remains in the store. So the spent. Yes, good, William. Sorry, I cut you off there before something even came through. Maybe there's a bit of a lag on the YouTube chat. Like I said, I'm still getting used to this. This is very, very new to me, this whole YouTube live thing. So do bear with me. Good. So that's your residence time. Now, in between this, obviously, we've got it stays in the store. We know it's locked up in these stores, but carbon will never remain in a store indefinitely. It doesn't matter if you're part of the slow geological cycle, which is what we're going to come on to tonight, or you're part of the fast biological cycle. It will move. It just takes varying degrees of time for the different stores and via the different processes. So there are processes that will move carbon from these stores and into other stores like this. So as long as you know the major stores, you know how much is within your most common stores, whether it be vegetation, you know that there's spatial differences in the amounts stored in different areas of the terrestrial biosphere, and you know the names of the processes that move carbon from one store to another, and how much in gigatons per year. The initial stages of the carbon cycle, so your inquiry question 1, you've got basically the essential knowledge that you need. And that stuff carries right through to inquiry question 1, inquiry question 2, and definitely in inquiry question 3. Inquiry question 3 gets a little bit more technical in terms of linking the carbon cycle and the water cycle together, but that's nice and easy. Okay, I'm sure you'll all be very competent with that. So now we know our stores, what we're going to do is we're going to look at some of the processes. So tonight I thought we'd focus on the slow geological cycle. Yeah. And then next week what we'll do, we'll go through the fast biological cycle, because that has slightly more intricacies and slightly more variation in what we can talk about. But tonight, let's go for the slow geological. Right. So just in terms of the way that I'm going to teach it, and this is the way that I teach it in my college and the way that I teach it as part of my online programs, I deliver content with exam questions in mind. Okay. So your big transition from GCSE to A level is going to be in terms of the application of the knowledge that you've got. So it's no longer going to be good enough for you to just memorize all the content. When you're memorizing the content, you've got to memorize it with a view to using it in exam style questions. Okay. So you've always got to think, when I'm taking in this content, what's its importance? So say I'm learning a process. What's its importance, and from what perspectives. Now I can come on to perspective stuff because I do a lot of that in my teaching, which is perspectives specifically related to 20-mark questions. That's one of the specialties I've got, is in sort of breaking down and increasing student competency in 20-mark questions. So the slow geological cycle. So let's say we start, just the camera, sorry. We'll start in the lithosphere. So we'll start in the lithosphere, which is in rock. So I've no doubt that in lower sixth, the majority of you have probably done tectonics. So the lithosphere, you just want to imagine it as crust. Yeah, that's it. It's either oceanic or continental crust. That's the easiest way to think about the lithosphere. So you know that the lithosphere doesn't remain still. It's constantly moving, and that's because of a combination of factors: convection currents, slab pull, ridge push. These are all the things that we can talk about with that contribute to the movement of the lithosphere. Now, as we know, the crust, the entirety of the tectonic plates, they interact with one another. So let's say this is some oceanic crust, and this comes across some continental crust, and here's the landmass here. We know that, and you can write this in the meeting chat, and I'll give you a little bit longer. We know that what's going to happen when some oceanic crust approaches some continental crust. We know we're going to get what process, or what's going to happen. So again, just type it out in the meeting chat if you can remember this from tectonics. Basic stuff, key stage 3 stuff. Brilliant, well done. So we know we're going to get that subduction, don't you? Yeah. And with that subduction, we have, yeah, good. We have heat and we have enormous amounts of pressure. Now it's this heat and it's this pressure that then leads to decreases in density. Yeah, so when you heat something up, you will decrease its density. And when you decrease its density, it will then start to rise. So this is when we have magma moving to the surface. So this should anyway be all very familiar to you from tectonics. Now, again, with heat, there's a relationship between heat of something and gas content. So as this is happening, what will also be released is gases in the form of CO2. So as well as the magma rising, there will be gas or bubbles of gas that are also rising to the surface. And then eventually what will occur is an eruption. Now, the first process that I always teach with this is that this is known as volcanic outgassing. Yeah, so it's volcanic outgassing. And this happens at a rate of around 0.15 gigatons of carbon per year. So very, in comparison to other fluxes. So that's your flux and that's your flux rate. Yeah, so your flux rate is always presented in either, well, various ways. A lot of centers will teach it as gigatons per year. Some people go petagrams per year. It means exactly the same thing. And out we come. Yeah, so out comes the carbon. So we've got CO2 gas, which contains carbon. We've also got lava, which contains carbon as well. So that's two ways, basically, that carbon has gone from the lithosphere, where the vast majority of carbon is stored, and it's making its way to what looks like up here, the terrestrial biosphere. That's the terrestrial biosphere, sorry, and this is to the atmosphere. So I'll go through what's really important to obviously keep inside your knowledge banks. So you've always got to say in the carbon cycle, where's it coming from? Where's it going to? How much is moving? And in what form? Yeah. So if we're putting that formula into a paragraph, let's say, it will be we're moving from the lithosphere to the atmosphere at this rate per year in this form here. The lithosphere, sedimentary rock, subduction takes place, volcanic outgassing occurs at a rate of 0.15 gigatons per year. That releases CO2 gas into the atmosphere, and we've increased the atmospheric concentrations of carbon. Okay, so we've got increased inputs of carbon into the atmosphere, increased outputs of carbon from the lithosphere. So that's our first stage in the slow geological cycle. Now, as you know, crust moves at millimeters per year. It's a very slow moving process. So this is part of the whole slow geological cycle. So this is the reason why when carbon's held in the lithosphere, it's held in there for around 100 million to 200 million years on average. So this cycle is a very long cycle. Okay, it takes a long time to put it lightly. Right. So now we've got our CO2 in the atmosphere. From there, CO2 can bind with or can react or dissolve into other things in the atmosphere. So if we consider that CO2 gas can then dissolve into water that is also in the atmosphere, what can happen then? So again, there's only two of us, but I think you're probably going to be quite interactive. What does that make? So what does that make? If we have CO2 dissolving into water, what will that then produce when CO2 dissolves into water? What does that produce? Very nice. Yeah, weak carbonic acid, otherwise known as acid rain. Yeah, with a pH of around 5.6. So we're slowly now thinking about, right, so carbon's moved into the atmosphere. We know it won't remain there. It's got to go somewhere else next. So it moves into the water cycle, and then it falls as acid rain. So our writing seems to be cutting across. All right. Now that then might come into contact with a calcium carbonate cliff. Yeah, so it comes into contact with a calcium carbonate cliff, or like a limestone cliff. And those of you that are watching that do coasts, you'll know exactly what happens next, which is chemical weathering. Yeah, so chemical weathering then occurs. So we go from here to the atmosphere. It then falls to the terrestrial biosphere, where it's then sort of becoming into contact again with the lithosphere, but it's surface level lithosphere, and then chemical weathering will take place. So that process of chemical weathering is essentially acid rain dissolving lithospheric rock. So that calcium carbonate is dissolved and is carried off in solution. Yeah, so it breaks up into calcium and carbonates that's then carried by water. So again, in the meeting chat, in the chat there, where will it be carried to? So where's it now going to be carried to? So that weathered cliff, that weathered rock eventually makes its way into a river, which will end up where? Where's that going to end up? So pop what you think. Where's that going to end up? Give you a few seconds to bring that through. Fantastic. Okay, so we've got the oceans. So then that chemical weathered cliff moves down here and it moves into the oceans. So we have carbonates making their way into the oceans. So they're now available. Okay, now some of these carbonates will just precipitate. Yeah, so some of them will just precipitate. And what that means is they immediately currently when they're in solution, they're in what's called an aqueous form. They will then react in the oceans and they will form calcium carbonate solids once again. And when they precipitate, they will then fall. Okay, they will sink, and we'll talk about that in a bit. The other thing that can take place is that the carbonates that are released from the chemically weathered cliffs then are utilized by what are called marine calcifiers. And these marine calcifiers will utilize those carbonates to form their calcium carbonate shells, like their exoskeletons that they use for protection. But it is the fate of all living things that all living things will die. They will die, and they too will sink. Now what happens then is they sink to the ocean floor, and over time, these sediments and these shells and everything like that will make its way to the ocean floor, and then the process. Let's get my knees here, and then the process of sedimentation takes place, which is essentially compression and compaction. And there we have it. We are back in the lithosphere. Now, the percentage of this stuff that actually makes it down to the ocean floor is very small indeed. It's around 0.1% of all the carbon that ends up in the oceans actually makes its way down to the lithosphere. So once again, you can appreciate these things are happening at such slow rates, tiny amounts over time. And that's why this is called the slow geological cycle. So it's at this point where I get my students to think about, well, because we know this, we've got to think about the importance, I guess, of the slow geological cycle. Because a 20-mark question might ask us to rank processes in the slow geological cycle, or even consider the importance of the slow geological cycle in comparison to any of the processes or the fast biological cycle, things that are happening right now in our lifetime, or things that we can consider across our lifetime. So the easiest way to think about this is the slow geological cycle is probably the most important when we are considering how the cycle works over the longer term. And those of you that decide to do any further work with me in terms of, if you want to join one of my online programs that prepares you for the exams and prepares you to think in these terms, then we do loads of work on different perspectives that we can consider A-level geography from, because it helps you write your essays. So we've got the long term. It's definitely the most important over the long term, because this thing lasts 100 to 200 million years. So anything that happens along that time is just a very small fraction of the process that's basically taking place over those longer term timescales. We can also consider this at a spatial scale. Again, this is another perspective that I drill lesson after lesson after lesson in the college that I work in. Spatial scale. So maybe the slow geological cycle at certain local scales is one of the more important processes. Maybe at this scale here, when we're considering calcium carbonate cliffs, it's the most important. Maybe along here on the ocean floor, yeah, it's probably one of the most important. Maybe right here at this volcano. We can also consider it at the global scale as well, because it's the slow geological cycle that essentially, and we're going to come on to this, that essentially balances levels of, or maintains the dynamic equilibrium that the atmosphere is held in terms of storing carbon dioxide or in storing carbon as gas. Because this essentially is one ginormous negative feedback mechanism. Okay, if you want to do well in A-level geography, like I'm talking about, if you want to hit A star to B, you've got to become very comfortable utilizing this concept of negative feedback mechanisms and positive feedback mechanisms, and this whole fundamental idea of things existing in a dynamic equilibrium, this constantly shifting balance. So this is a massive negative feedback mechanism over longer term timescales, and I'll demonstrate why. So because we've suddenly had this increase inputs, the idea with a negative feedback mechanism is that an increase in something will then lead to a decrease in something, yeah, or it will bring the system back to equilibrium. So we've suddenly had from, because volcanic outgassing is this just enormous release of carbon into the atmosphere in the form of CO2. Yeah, boom, suddenly the balance is shifted. So the system works to rebalance itself. So how does it rebalance itself? One of the ways, because we've lost some carbon from the lithosphere, so we need to get it back. We've got extra in the atmosphere, so we need to rebalance that. So the extra in the atmosphere is balanced by the fact that it'll latch onto CO2 and will just make more acid rain, because the more CO2 that's available, the more acid rain we will make. So rain will become, more acidic, and there'll be more of it. So that means more calcium carbonate cliffs, more limestone cliffs experience chemical weathering. More carbonates make their way into the oceans. More carbonates make their way down to the ocean floor, and therefore more is then added to the lithosphere via that process of compression and compaction. Now, we're not talking about this happening over a decade or so. The whole system takes around 100,000 years to rebalance. So if we're considering the importance of this thing over that time span, we'd say, yeah, it's probably considered one of the most important processes, or still a series of processes, that keeps atmospheric levels of carbon dioxide in balance or in check. Now, this does take 100,000 years to rebalance. Then what you'd probably say is over shorter term timescales. So over shorter term timescales, you've got other processes that will rebalance to a greater degree, or it will seem like they're more important when we look over like a daily time span, or like a monthly one or an annual one. There might be more important things. So with A-level geography, you're always talking about what perspective are we looking at this content from. Okay, so that is the slow geological cycle, and that's all the content that I wanted to talk about tonight. So I hope that landed well. Like I say, I'm experimenting massively with this live thing, so it's not something that I've fine-tuned just yet. Like, I already know from looking at the video, it's a bit dark. Yeah, so I need to look at something that's slightly more high definition. I need to look at lighting, but hopefully you found that useful. So what I'm open to now, and this was the intended plan, is I'm just open to a Q&A now. So anything that anyone's struggling with, it might be NEA, it might be another module, you might have an idea for something that you want to do in one of these live sessions, something that I can go through, something that I can go through right now while I'm on the whiteboard. Literally, you can treat this live session, once I've done the content, as a little bit of an A-level geography clinic. Yeah. Thank you, William. You are more than welcome. Thank you very much. I'm glad it's worked. So if you tune in next week, then you'll have a great idea of like what comes next. So like where the linkages are between this cycle and the fast cycle as well. So does anyone have any questions at all about what might come up? Or I think most of us at this stage, at my college, my students have handed in their NEA now, but some of us still might be working on it. Currently struggling with essays, and your videos have helped. NEA is a bit of a struggle to be getting through it. Yeah, the best. Look, thank you for the advice on the. Thank you for the feedback on the videos. There's going to be more coming. The videos. It's just I work full time, you see, so I don't have a lot of time to create the videos. So it's one of those. I've got to think about what videos to prioritize, and it takes time to edit them. But there are videos coming. I will be producing more videos, particularly. You'll have noticed a lot of my videos are exam technique focused, which I think is of most use. Content is also going to be there, but you can get the content from, I don't know if you've all seen that I've got you can basically sign up to my online study course for free. Geological cycle is a negative feedback loop. Yes, it is. Yes, the slow geological cycle is one big negative feedback loop. So I can go through that again. So think of it as your negative feedback loop rebalances the system. Yeah, it rebalances the system. So we've suddenly had an increase in CO2 in the atmosphere. So we need to make sure that we can rebalance that. We need to bring the CO2 levels down in the atmosphere. So that means, okay, here's how it does that. It dissolves in water and then falls to land or falls to the sea. Then what we do is we need to rebalance the levels in the lithosphere. So that's how the chemical weathering works, and it brings it back and precipitates, and the carbonates fall to the floor. Okay, the ocean floor. So that's why it's a negative feedback mechanism, because it's rebalancing the entire system. But it's a slow one. It's a slow rebalancing, and theoretically it's 100,000 years. So it's not as simple as you would think, or it's not as quick. But there's all sorts of things that happen in between that could upset that rebalancing. Okay. Any other questions? I'm happy to call it a night if people have not got questions, because there's only 2 I can see on the screen from I think that means 2. The people image I think means 2. So if there's no other questions, I'm happy to call it a night, and we'll call it a day there. And if there's anything you want to get in touch with me about, best way, comment on one of my videos. I do monitor the comments, and I do comment back when I've got time. So if there's anything that you need to know, or anything else that you want to ask me in the comments section, because that's usually where I'm able to answer. Anyone got anything they want to know? NEA related, absolutely anything. What I'm hoping is the numbers grow, and then the questions will grow, and then the lives will potentially flow a little bit better. Not seeing anything coming through. Okay, let's call it a night there. Thank you very much for joining. Really appreciate your time. And like I say, I hope it's been useful. So like I say, if you tune in next week, you can get access to more of this, and we'll do the fast biological cycle. All right. So thank you very much. Good night. Godspeed with all the A-level stuff. It's not easy. No, thank you very much. And I will catch up with you all soon, hopefully. Thank you. Thank you for joining.